Imagine this. You're a nerd in high school. You've always been good at math throughout your entire life. You've breezed through geometry, algebra, trigonometry, and pre-calculus, and have been encouraged by your pre-calc teacher to take the infamous class known as AP Calculus. You already know about the infamous reputation that calculus has, but since you persevered through pre-calc and got a good grade in it, and are oblivious to the danger right in front of you, you tell yourself, it can't be that bad, right? The answer to your question is, yes, it is, indeed, that bad. You have no idea about how difficult calculus is. You poor, sweet summer child. Anyways, because calculus is, indeed, extremely difficult, perhaps you should get a glimpse of how calculus works before you take AP Calculus next year. Well, unless you don't hate yourself, and you just choose to take AP Statistics instead. So, here's a rundown of the bare bones basics of AP Calculus. This should give you a rough idea of what to expect if you choose to suffer, enjoy it next school year. And maybe, if you're into that sort of thing, you can get a good score on the AP exam in May. Let's create a hypothetical situation. Suppose a car was driving down a road. It has been on the road since 1 p.m. and has not stopped moving since then. Let's say that at 2 p.m., the car has traveled a total of 40 miles, and it is currently traveling at a speed of 34 miles per hour. The 40 miles traveled after 1 hour of driving represents the position function of the car, and the 34 miles per hour speed of the car represents the velocity function of the car. The velocity function is the rate of how much the position function increases or decreases at any given time. The velocity function is the derivative of the position function. When the position function and the velocity function are graphed, it can be found that the velocity function's y value when x equals 1 is the same number as the rate at which the position function is increasing when it is at x equals 1. This is what a derivative measures. It tracks the tangent lines, or the amount the original function is increasing or decreasing in value at a specific time, of any point of the original function. Now, let's include the fact that the car is accelerating at a rate of 3 miles per hour at 2 p.m. This new rate of change acts as the acceleration function of the car. The acceleration function is the derivative of the velocity function, and it is also the second derivative of the position function. Knowing the first and second derivatives of a function can be used to determine useful information about the original function, like the relative or absolute maximum and minimum values it can produce, and when the function changes from being concave up to concave down, or vice versa. There are various methods that are used to find derivatives, or derivatives of derivatives, such as the constant rule, the trig rules, the quotient rule, and the most important rule of all, the chain rule. More methods exist, but you will learn about them later on in the class. I don't have time to explain all of them in this video. Now, let's talk about integrals. Let's return to the hypothetical situation from earlier. Suppose you knew that the car's speed was 34 miles per hour, as well as the velocity function of the car, but you did not know what the position function was, and you wanted to know the car's position at 2 p.m. In order to find the position function, you must use a process called integration on the velocity function. Integrating the velocity function will find its antiderivative, which will be the position function. If the velocity function is the derivative of the position function, then this also means that the position function is the antiderivative of the velocity function. This also means that the velocity function is the antiderivative of the acceleration function. The theory that states this relationship between derivatives and integrals is called the fundamental theorem of calculus. Since integration is the opposite of finding a derivative, to find the integral of a function, you would do the opposite operations that you would have done if you were finding a derivative instead. Have I lost you yet? No? Sweet. That's good. Isn't learning fun? I think it is. Something else to keep in mind is that because there is no way to reverse the constant rule, a plus c must be added to the end of every integral in order to compensate. Don't forget the plus c. Now, let's say you knew the graph of the velocity function, but not the function itself, and you still had to find the car's total distance traveled at 2 p.m. Impossible, right? No, it's actually possible to solve this conundrum. You can estimate the total distance traveled by drawing several rectangles underneath the graph's curve and then finding their total combined area in order to get an approximation for the total distance traveled. This is called a Riemann sum. They are cool. Integration can be used to do other cool things, such as accurately finding the volumes of complex 3D objects, or finding the length of a complex curve between two specific points. Just keep in mind that learning how to do things like these is very difficult, and most people that learn calculus will have trouble. Are you still paying attention? Yes? That's good. Now, hopefully, you still have a desire to take AP Calculus instead of AP Statistics. Let's get back on track. The AP Calculus AB class ends after learning about derivatives, integrals, and another topic called limits. Limits are easy to learn and understand compared to the rest of calculus, so if you were smart enough to pass pre-cal, you should not have a problem with learning limits. They won't be covered in this video. Sorry. Anyways, AP Calculus BC, unlike AB, goes on to teach some extra topics that you should be aware about. Let's talk about them now. If you still haven't left the video yet, then I guess that means you're actually interested in calculus. That's good. You're not going to take AP Statistics.
Oh, brother, this guy stinks!
Now, the AP Calculus BC class covers the extra topics of series, polar graphs, and parametric equations. Series are special equations that use summation to constantly add the same function to itself over and over again, with the n value of the function increasing by 1 each time, until it adds up to either positive or negative infinity, or an actual number. Series that result in positive or negative infinity diverge, while those that result in an actual number converge. There are various types of series, like the P-series, the geometric series, the alternating series, and the infamous Taylor and Maclaurin series that are the banes of all AP Calculus BC students. Watch out for those. All of these series have special rules about what needs to be done for them to converge or diverge. Some series also only converge on a specific interval, and a couple only converge conditionally. Next, we have polar graphs. Unlike a normal graph that displays data on an x-axis and y-axis, polar graphs show data by the radius and radians of a point from a trigonometric equation, instead of the coordinates x, y. Polar graph coordinates are r, theta. You are able to convert normal coordinates into polar coordinates, and vice versa. Polar graphs are confusing. Heck, even I don't understand them that well, and this topic will most likely be skimmed over for only 2 weeks or so at the end of the year. Hopefully your math teacher can help you more than I can. Finally, there are parametric equations. Remember the hypothetical situation we made with the car? What if, instead of only measuring the distance traveled by the car since 1 p.m., we measured both that and the amount of gas that is in its gas tank, at the same time, with both functions using the time since 1 p.m. as their input values? Well, that can be done by creating a parametric equation. The x-axis measures the total distance traveled since 1 p.m., and the y-axis measures the amount of gas that is left in the car as it steadily decreases. Notice how the time since 1 p.m. is not being tracked on the graph. But if you wanted to, you could remove the parameter and turn the parametric function into a normal function. That exists as an option. Parametric equations are extremely useful to analyzing the correlation between two different measurements that use the same thing as their independent variable. In other words, parametric equations are able to track and display the relationship between two y values that use the same x value. Well, that was a handful. So, AP Calculus is rough. You should expect it to be rough. Do not go into this class expecting yourself to breeze through it, because trust me, you will struggle. If you wanted to take an easy math class after pre-calc, you would take, you know what, I'm not even going to say it. You already know about what class I am talking about. The topics you learn throughout AP Calculus are integral. Ahem. As I was saying, the topics you learn in AP Calculus are integral to the foundations of math. College majors such as computer science, biology, mathematics, physics, and engineering all require you to fully grasp calculus. And for selfish reasons, the jobs you can get with a degree in one of those majors are very well paying. That's the reward for suffering in, I mean, enjoying calculus. There are, of course, things that I did not cover in this video, such as Euler's method, implicit differentiation, L'Hopital's rule, and various other things. But if you take AP Calculus, your math teacher will teach you about those. And that exam that the College Board offers? Don't worry about it too much. The curve on that exam is so beneficial. Getting a 60% on it will give you the maximum score, due to how many people do poorly on it. And you can even pass it with just a 40% score. So, what are you waiting for? Go sign up for AP Calculus. And don't you dare take a P statistics.